Electric field characteristics. So to understand the electric field, we have to go through some of its characteristics as well as the definition of the electric field. So what we're going to do here is that we're going to go through the electric field characteristics, including defining the field of a point charge. Okay, let's go for the first one. Since there are two types of charge, there are two types of electric fields. We do not want to draw the field pictures from lecture 2.1. That's just crazy. So if I just have images of them, so I'm going to just put them right in here. And I mean, I don't want to draw these. That's painful. And it's not useful either. So we need a better way of drawing electric fields. So the issue here is that the field points are infinite in number. Which we have to change. So what we do here is that we draw an effective picture of field lines. But these are also infinite in number. So what we have to do here is that we have to have an effective model that draws a finite number of lines. So in this situation, what we do here is that we draw a finite number of field lines to give a sense of the field. So what we'll look at here is that they all have to follow Coulomb's law. So these field lines are based in Coulomb's law. Now, I want to be careful when I say this, because not all fields drop off as 1 over r squared. But what Coulomb's law is saying is this, that the electric field vector must be proportional to the electric force. And I know that the electric force in this case is proportional to 1 over r squared, and this is r. So note, I can only say this for effectively a point charge. But that's not the important piece here. The important piece is this guy right here, that the field lines of a point are symmetric. So when I think about a field, instead of drawing this atrocious picture, what we draw here is we come in here and we draw a charge. And we could say here, and then over here, I'll draw a negative charge. And they have to have different colors, or they have different fields. And what you're seeing here is that now I start to draw in fields, lines. They're not an infinite number, they're a finite number, but what they're telling us here is that they're giving us information about the strength of the field. And that's what we really want here. So when I look at a negative charge, it looks like the field lines are going into the charge. If I look at the positive charge, it looks like it's going away from the charge. That's a bad way to think about it, and I'll get more into that. But these guys are called field lines. So now let's start to interpret this picture, because there is a lot of problems with this picture. And there's a lot of misconception, which I want to try to clear to the best of my ability. So now let's go to the second one. So one must be careful when interpreting the meaning of these sketched fields. So this is key. The field line starts at the charge and goes outwards. That's tricky. Okay, so why am I saying that that's tricky? It's because of the language that people use. They'll say that the positive charge here is a source, like somehow it's emitting field lines like a source of water, and that the negative charge is a sink. Everything is flowing into it. That's incorrect. And like I said, it's dangerous to think that way. So that means right here, this is where the field lines originate from the charge. The same thing happens with the negative field line. It's not coming from infinity, it's starting at the negative charge and it's going out. So, and then another thing that we want to be really careful, we say here is that the positive field do not flow outwards. The negative field does not flow inwards. Those are misconceptions. Just because you may want to put a picture like that in words, it's incorrect. Okay, so these statements are incorrect. These are incorrect statements. It's a common misconception. There is no flow of electric field lines. And I don't care what anybody online says, that is not correct. Once an electric field is established, it's there. It goes through all of space. I mean, there is an initial startup where it moves at the speed of light. So to try to get a little bit more into this, we then go to the next characteristics. The field strength is solely determined. No, that's not the way we spell it. By the line density. Now remember, every charge has an infinite number of field lines. So even though I may have a lower charge, it still has an infinite number of field lines. So once again, we are drawing an effective picture using finite line densities. So like I said here is that every charge has an infinite number of field lines. And you know what? I should have said this in big words. Every charge has an infinite number of field lines. We draw an effective finite line density model to tell us about the strength of the field. So here we go. So what you could imagine is that I have the following thing. I have a field, a number of field lines that look like this. And what I need to do, everything is relative. So now if I have a different field, and what I'm seeing here is that the line density is higher here, and over here it is lower. So then that tells us the relative strength. So therefore, if I have a lower line density, that implies that I have a weaker field strength. If I have a higher line density, that tells me I have a stronger field strength. And that's a finite number of lines. So one example that we could give here, which gives us two different things here. And I'll try to show both of them. So imagine that I have a charge now. So suppose I have a negative charge, and this negative charge only has one charge value. I have another negative charge, and look that I'm trying to draw them the same size because charge is not about size. This guy has twice the number of charges. So what we're seeing here is that now we scale it. What I'm going to do here is that I'm going to say, this is the charge, and then I need to compare this to the line density. So if I have one negative charge here, and over here I have two negative charges, one way to model this is to say that if I have, let's say in this case, one negative charge has four lines, then I'm going to come in here and I'm going to say, okay, so here's my field. So my field only has four lines. Now, if I look at this negative charge over here, then this guy should have 8 lines. So now if I start to look at what the field lines are looking like, they're looking something like this. So remember, they start at the charge and move outwards. So clearly here, a higher number of lines implies a stronger, a lower number of lines implies weaker. But there's another piece that we should look at. And the other piece here is that let's look at the point P. So if I look at a point P right here, and I look at another point P right here, what you're seeing here is that look at the spacing between the lines. So if I look at the spacing between here and here, note that they're spread out more. So right here, you're seeing that they're spread out more. This further indicates that it's a weaker field. But if I look at the same distance right here, you could see that that distance is closer. So I have a higher line density. But the thing that's interesting about this, so here we're going to say here is that this guy is stronger here. But as I get farther, look what happens to the line spacing. So as I get farther, you could see that right here, they spread out. And so therefore, that's a weaker field at that. So there's two ways to look at the line density. One, there's less lines. Two, they're also spread out as they move out, therefore indicating that the field is dropping off. So now we're ready to define what the electric field is. So we are now ready to define the electric field. So what we're going to have to do is that we have to separate out the two charges that are interacting. And we actually give them names. So one we call Q source, which is the source charge, versus the test charge. And typically we write a little q for the test charge. And then this is the charge that tests the strength of the electric field. So let's do that now. So when we have an electrical interaction between two charges, we sample the strength of the field by placing a tiny test charge in the field. Okay, so remember, if we're talking about the electric force, that's what we would do, but that's not what the electric field picture is. So we want to do two things here. So what I'm saying here is that to test the strength of the electric field, one places a test charge to measure the force applied to it. So now I have a force picture. So I imagine that I have a test charge. So not a test charge, a source charge right here. And what we're interested in doing here is that we want to test the strength of this field. A good analogy would be a thermometer. When you use a thermometer, what you're doing here is that you're sampling the energy inside the body. But it only takes a tiny, tiny bit of energy away from the body. The same thing happens with a test charge. I imagine that I have a field. And as we said before, I must have two interacting fields. So then I have a test charge right here. And so when I place this test charge right here, because it's like the thermometer, what it does here is that it experiences an electric force. So we know how to write the electric force. The electric force says that it's a vector. And if we're talking about point charges, we know how to write that. This is Q test. This is Q source. And then this here is the distance that it's from. And of course, we need that direction. So now what we want to do is that we want to remove the test charge. So if I remove that test charge, I still have this system here. So I'm going to come here and I'm going to copy this, and then I'll modify it a little bit. So I still have exactly the same setup, but now there is no test charge anymore. There is no electric force. what we do here is that we put a little imaginary point, a field point. And when we're looking at that field point, what we measure here is the electric field. And so how we get the electric field at point P here is that we then say that we have this thing called the source. And when I look at the electric field source, you could see here is that in order to get rid of Q test, I have to divide the force by Q test. So when I do that, what ends up happening is that we remove all information about Q test, leaving only the source details. In other words, it's the electric field. So then we could come over here and define it. So the electric field of a point charge is then reads like this. We say that the electric field of a point, let me do this slightly different, that the electric field of a point, we said here, it's the electric force divided by Q test. And then this isolates the source. And when we go and we look at this thing, we see here that we get, by the way, I should have written this and I didn't. This is the electric field of a point, which then is 4 pi epsilon. And I divided out Q test. So then this becomes R squared and the denominator times Q, the source, and it gives me that. This is the definition of an electric field of a point. Over here to the right, E source equal to the force divided by the charge, that is the electric field. So when I look at the units of this, you can see here is that the units of the electric field is a unit of force divided by a unit of charge, which then is a Newton per Coulomb. So the electric field clearly depends on charge and distance. The electric field depends on charge and distance to the point P. So let's look at these guys here, and they go something like this. I have charge dependence Q. So what does the electric field tell us? So I'm going to imagine that I have a field that looks like this. I have a charge that has just a single charge value. So I'm going to say that I have a single positive charge. And the way I'm going to define this guy here is I'm going to say one charge gives me 4 fields like this. So in other words, this charge I'm going to call Q. Now, if I take a different charge, and in this situation, I'm going to say that this charge here has a lot of charge. So if I come in here, you could imagine that I have 4 charges. So that means if this has 4 lines, this has to have 16 lines. But we're not going to draw 16 lines. all we're going to show is that there is a lot of field lines. And what we're seeing here is that in this situation, we clearly have a much bigger charge. So now what I'm going to do here is that I'm going to pick a point P. And I'm going to pick the point P where I only focus on the charge. So then the distance from here to there is R. So what do I see? Well, if I have less charge, I have a weaker field. So therefore at point P, I'm going to have a field that's not as strong. Because I have a lot more charge, then my electric field here is going to be a lot larger because it's directly proportional to it. So in other words, I can say this: if I have less charge, then what I expect to see is a lower line density, but a lower line density tells you that it's a weaker field strength. And then according to what we wrote here, this is going to be 4 pi epsilon r squared. Well, the reason why is because I had a smaller charge, so therefore I have a smaller electric field. Now I can do the exact same thing for the other one. So I'm just going to copy and paste it and modify it. So if I do the same thing here, now it's not about less charge. I have more. And I don't have a lower and I don't have a weaker. I have a higher line density, and therefore I have a stronger field strength. And so if I come over here, then I clearly see that I had a bigger charge. So therefore, my field strength has to be larger. That's what I mean about the charge dependence. The other thing that we want to look at is if we want to look at the distance dependence. So what I'll do here is that I'm going to set up just a field with the same, excuse me, I want to set up two charges with the same amount of field lines. In both situations, which means in this case, let's say that we have three, that represents three positive charges. So then I'm going to I'm going to copy this because I want to set up the exact same situation. So what you're seeing in this situation is we're seeing this. This guy has a charge of Q. This one has exactly the same charge. So now charge is out of the picture. So what I'm going to look at is that I'm going to look at a point P. If I look at a point P here, that tells me that this distance from here to here, this guy is going to be little r. On the other hand, if I move my charge point, my observation point P, well, this distance here is going to be really big compared to the other one. So I have a large distance. So what we would expect, well, if it's closer, then I would expect that the field here should be larger. It's going to interact with it more. If I'm farther away, the field should be smaller. So then I play the same game as I did over here. And if I look at this, all I have to do here is just modify it right here. So in this case, we're not talking about charge. what we're talking about is that this guy, it's about that it's a closer distance. And if it's a closer distance, it's going to have a higher line density and therefore a stronger field. So in other words, this is going to have a higher line density and therefore a stronger field. So I got to modify this. So if I modify it, what I'm really seeing is that the charge now stays the same in each situation. The difference here is that this is a smaller r, therefore I get a larger electric field there. So now if I just modify this just a tiny bit, I do the exact same thing. So it's not closer, it's now farther. And it's because it's farther, it has a lower line density, telling me that it's a weaker field. And the reason why that is because now the radius, or the not the radius, but the distance is in the denominator, which gives me a smaller electric field. So one last thing here. Since electric forces and fields are proportional, if more than one source charge is present, the net electric field must be calculated using superposition. And what I mean by superposition, it's the same thing as Newton's second law. So it says here that if I have multiple forces acting on it, so if I have multiple discrete charges, they don't even have to be discrete, but I got multiple of them, that this here, this is the sum of all E fields, right? And let me be careful. All individual E fields. What superposition says that I can replace all of these with a single electric field. And so what this is telling me here is that this guy right here is a single resultant. And what that means here is objects, charges do not fill individual electric fields. They feel only the net force. They respond to the net force. So what this implies here is that one must apply superposition when several charges are acting. And to give you a sense of this, what I want to do here is that I want to give you an example and remind you what do I mean by superposition. So what I'm going to do here is that assume all charges have different signs, but the same magnitudes. So then what I want to do here is that I want to rank the field strength of E net. So this is really arbitrary, and I'll say E net at the origin. So let me set up one of these and then let me copy it. So let's say I do this. So the colors don't matter, but let's say that I'm always going to pick a red one here. I'm always going to pick a blue one right here, and I'm always going to pick a green one. So when I look at this guy, then I'm actually seeing something like this here. So I'm going to pick 4 situations and just kind of play with them just to remind you about superposition. So now I'm going to assign the values. So they're all equal distance to the center. So I'm going to say that right here is going to be my point. Let's see, this is going to be the point P. This is my point P everywhere. So we want to rank the fields at point P. So I'll label this as 1, 2, 3, 4. So here we go. What happens if I have positive charges everywhere? What would I see? Well, if I draw a free body diagram of the fields, then this is what I'm seeing. Well, first of all, note that the red and green are symmetric. And because the red and green are symmetric, we know that they have no x component and there's only a y component. So right away, I can conclude that. But since these are fields and we haven't done that, that's a positive test charge right there. So then that force applies an electric field that one. This one applies an electric field in this direction, and therefore I have an electric field here. So it turns out that then these guys sum to 0. So then I could see that the net field at 1 must equal the strength of one of the fields. Now, what happens if I do this? So if I do the opposite, and let's say that I put positive and negative like this, what does superposition really tell us in this? Well, I'm looking at this and I got to look at what those charges are doing. So what's the negative charge doing to the test charge? It's moving it to the right. What's the red doing to that? It's moving it to the right. And then the blue is then doing what? It's pushing it down here. So when I look at the net field here, that net field is in this direction by superposition. So this is the net field at 2. And right away, you could see that 2 has to be bigger than 1. What if I did something differently? What if I don't know, what if I have um, positive, positive, negative? Well, again, from symmetry, we could see here that the charges on the x-axis will then all be um, canceling out. So by superposition, I can see that I only have one field that's moving like that. So in this situation, I could say that the magnitude of 3 is then only going to be 1 unit of the electric field. And then finally, I could pick a different situation. Maybe I pick, I don't know, what about no, how about this? What about positive, positive, negative? So what do I see here in this situation? So again, that's a positive test charge right there. So that means here that to the left, I'm going to have a red field pulling it in that direction, a green field pushing it in that direction, and then finally a blue field coming like that. So I can see here by superposition here that then this net field at 4 looks something like this. So ranking wise, we could see here. So if I now rank them, I could immediately see that the net field of 2 is the same as the net field of 4, which is then going to be greater than the net field of 1, which is equal to the net field of 3.